Okay, so we're going to start looking at some of the 4.2 stuff, section 4.2. This is going to be about two main topics. It's first bit's identifying absolute max and mins of a function over an interval, and the second part of this is going to cover something called Rolle's theorem. So we're going to write down a definition and look at a couple cases, and then after that we'll move on to some more examples until we get section done. So, first definition. This is going to be extreme values on an interval. So, this, we're going to have a little bit of setup here. We need to let f of x be a function on interval I. So f of x is a function on interval I, and we're going to let a be an element of I. And then we say f of a is the, so extreme values, this is going to refer to maximum, absolute maximum and absolute minimums on a interval. So if we have a function on an interval, we're going to say that f of a is the absolute minimum if, or we say of the function on the interval I, if the f of a value is smaller than or equal to all the other y values that come from the interval. And this is kind of the math way how we say that. So we say if you have this f of a and it's less than or equal to, you look at all the other x's in the intervals, f of x will be their y values. So you say this right here, f of x, represents all the y values that come from that interval. If your f of a is smaller than or equal to all of those, then it's the absolute minimum. And absolute maximum will be a similar statement. So we'll say this time if f of a is greater than or equal to all the other y values that come from the interval, then that f of a would be an absolute maximum of the function. We're going to write down a theorem, and then we're going to look at a couple cases. So we have this theorem. And this theorem says a continuous function we'll call it f of x on a closed interval we'll call it I, and say that the closed interval I starts at a and goes up to b. That takes on both a minimum and a maximum value in I. Okay, so let's look at a couple different cases. So we're just going to kind of look at this theorem first, kind of see how that works. Then we'll see if a few things that can kind of cause some issues with that. So let's say that we had a continuous function. So let's just say our continuous function looks like this. And let's say that here is our a value and here is our b value. So a has a y value here and b has a y value up here that's a little bit higher. So what we're going to do is we're going to look at all the x values between a and b, and for each of those x values we're going to look up and see what y value do they produce. And the largest y value, which to me looks like it would occur right here at B. I think that's the biggest Y value from A because A is here, it's not quite at B. All these other ones are smaller because it goes down. When you come back up, B's Y value is way up here. So that's going to be our absolute maximum. And then the smallest Y value is going to be right here at the bottom of this dip. That will be our absolute minimum. And if you're a continuous function, over an interval like this, you're guaranteed to take on both an absolute maximum and an absolute minimum. So if we had a different continuous function, maybe it's got a little more kind of, let's draw it where it doesn't go back on itself, but maybe it has a couple more like wiggle shapes in it. And we say, okay, A is here, B is out here. A's Y value is about right here. B's Y value is there. We'd say, okay, this is continuous, so we're guaranteed a max or a min. The largest Y value looks to me like at the tip of this peak. I think that's the absolute maximum. And then I think the smallest Y value that's obtained is right at the bottom of this trough, which is the slightest bit smaller than the B value. I think that's our absolute minimum. So again, what that means is for all the x's, starting at A, stopping at B, and in between them, the absolute max is the largest of all the Y values for those x's. The absolute min is the smallest of the Y values that come from all those x's. Now, there's a couple weird cases if stuff's not continuous, like maybe if we had a removable discontinuity, so we had like a parabola shape, but the Y value is missing there. Let's say the actual function value is down here. If you look from A to B, A is here, B is here. I think this point over that interval, I think this point here, that'll be the minimum value. That'll be the smallest value obtained on the interval because A is higher than it and B is also higher than it. And all the points in between are higher than it. So that's the minimum. But the maximum would be where the point is, but the point's missing. And since the point's missing, there's not a next closest number. For example, let's say that the Y value here at this point was 5. Let's just pretend that that's 5. If the value 5 is missing, you say, well, what's the next closest number to 5? Well, we could say, well, it's like 4 point, and we'd have to start writing 9s. And at some point, we'd have to stop writing 9s and say, okay, there's my closest number to 5. It's 4.99999. And however many 9s I write, I can always put an extra 9 after it. And that's a number that I missed, that I didn't include, that's bigger than the current one I'm claiming is the max. And that causes an issue. So there's not really, if the value that's going to create the maximum or the minimum is missing due to like a removable discontinuity, there will be no, like there's no maximum over here. Now, if the removable discontinuity happens somewhere in the middle, like maybe you're a kind of a function like that, and you got your missing point and the Y values here, and A is over here and B is over here. Like we could say, well, A's Y value is here, B's Y value is up here, so the minimum value looks like it's down here, so there is a minimum. The maximum looks to me like it's way up here at B. So if that removable discontinuity happens somewhere in between the minimum and the maximum value, you don't have this issue. It's only if this gap here occurs at what's going to be the max or the min that you have this possibility of there is no max or min occurring. Another thing that can kind of happen is if you have an infinite discontinuity. Basically, if you have like a vertical asymptote out here at B and your function is running up along B asymptotically, so like A is down here, then it just goes up towards B. You could say, well, A maybe is the minimum value. A is the lowest value on this. So maybe there is an absolute min here. But since heading towards B, it just heads upwards higher and higher and higher, there's not going to actually be a max, because we run into kind of a similar problem where whatever I claim the maximum is, however big I claim the maximum is, this will go beyond it. And I really can't write down that this is the maximum due to that problem. So if the function is continuous, then you're guaranteed a max or min, because you're guaranteed there's not going to be any holes that you need to account for, and there's no vertical asymptotes causing problems. If you have non-continuous functions, sometimes it's okay. You can get a max and min if the hole isn't right at the edge of what you need. Sometimes it causes problems. Vertical asymptote, that can cause an issue. So these are just some things that if you're not continuous, these are some of the issues you can kind of bump into.